Good evening, folks. Thank you for coming along to our November meeting. I'm hosting this evening because Pete has been unavoidably detained with a domestic crisis. It's nobody's injured or hurt, but it needs his attention. So I have the pleasure of hosting the meeting tonight, and the meeting will follow the format. So we've got an excellent talk on ice giants by Pauline MacRae from Haas, and then after the intermission, Stuart's going to do his space news, and Mick will do the Murray Sky at night, and then I'll run through a bit of club news at the end of the meeting. As last month, we're planning to have a meeting after to sort of try and help the sort of social gathering side of it. So you're all more than welcome to come along to that. There'll be a link to it copied into chat at the end of the meeting, and if you just give us a few minutes, if you click on that link and follow that link, and you just give us a few minutes to close this meeting and open that one, we'll join you for that. Anyway, we've got a really good talk tonight from Pauline MacRae of Haas on ice giants. And when I first saw this talk, I was amazed at the amount of information that Pauline had managed to gather together for this really excellent talk. And now, as you all know, Pauline's a very prominent member of Haas, and I asked Pauline what she did for a living as some form of introduction, and it took me about three attempts to actually say this word correctly. But Pauline is a qualified and soon to retire, actually, orthooptist. I hope I got that right. And not quite right. Sorry, Paul.
That's okay. Orthoptist.
Orthoptist, right. Okay, thank you. Which I'm reliably informed is basically involves correcting squints and that sort of thing. And Pauline's been involved for the last few years, actually screening children in nursery to pick this fault in their vision up quickly so that it doesn't impact on their education. So anyway, without any further ado, I'll hand over to Pauline. Let me just stop my share. Oh, first of all, I better just do a quick run through the Zoom controls, just in case anybody isn't familiar with them. Let's see if I can just get my slides to advance here. Yes, there we go. Right, first of all, as you know, Zoom is controlled by a panel along the bottom of the screen, and this allows you to, switch a microphone on or a video if you're a panelist or if you get promoted to that. But as an attendee, it allows you principally to change the speakers you use to listen to the presentation. So if you're watching this on a widescreen telly or something like that, you can listen to it on the speakers of that device. So that your audio settings principally allows you to do that. So next, and I see lots of people have already been using the chat, so there's a huge amount of messages on that already. But you can communicate with ourselves, the panelists, or all the people in the meeting by going into chat and typing in your message and pressing enter to send that message after you've sort of checked that it's spelled right. I normally forget to check the spelling of mine before I hit the enter, but anyway, that's my problem. But the most important thing with this, guys, is to ensure that you send it for the attention of, it's set by default to all panelists, but if you change that to all panelists and attendees, that will allow everybody in the meeting to see what's see what you want to say. It's the next thing as well, and what we would encourage you to do is with the to put any questions you have for Pauline in the Q&A, again by pressing the Q&A button, and then if you type your question into there and send it, it will we'll pick it up on our screens, and I think Donna's going to ask the questions this evening for Pauline, so as she did last month, and did a very fine job of that. So the next thing is, if you want to raise any of the panelists' attention because of some issue you've spotted or issue you're having, just press the raise hands button. We get notification of that, and we will enter into a chat with you through chat to sort your problem out. And if you manage to hit that raise hands button accidentally, you can simply press it again, and that will lower your hand and take it off the screen. And finally, at the end of the meeting, you can leave the meeting by pressing the red button on the extreme, or the red leave meeting button on the extreme right hand side of the screen. Also, you've got a green tab across the bottom, across the top of the page, and that's to its right hand side has a drop down arrow that has view options. If you're watching this and for some reason the display gets too large or too small or whatever, if you hit the fit to window button, which is the top option, you can normally resize it properly so it fits your screen. If you need to answer some emails or whatever, and you're using a single screen, if you can either exit full screen or continue to watch with it at 50% so you don't miss any of the talk. Okay, so right, sorry about that. I will end my screen share and hand you back to Pauline. Okay, over to you, Pauline.
Thank you. Thanks very much, Rich. Okay, let's see if we can get this all sorted. Good. Okay, well, thank you for that nice introduction, and thank you for asking me to speak to you. Now, tonight I'm going to tell you about the ice giants, which sounds rather like a Viking's tale, but actually refers to our two outermost planets, Uranus and Neptune. Most of what we know about these two planets comes from the Voyager 2 mission, which flew past Uranus and Neptune during the 1980s. Took advantage of a planetary alignment, which gave a gravity assist to the spacecraft so it could reach the outer planets faster than it would have otherwise. Astronomers are still working on the data returned over 30 years ago, some of which has proved difficult to interpret. However, with advances in experimental techniques, allowing scientists to recreate the intense temperatures and pressures expected to exist in the interiors of the ice giants, as well as state-of-the-art computer modeling, our understanding is improving. In addition, we're lucky to have the Hubble Space Telescope and also ground-based telescopes with adaptive optics, which have been able to photograph the planets in high resolution, allowing further study of the atmospheres and weather. And together with all these things, gradually, astronomers are beginning to appreciate some of the mysteries of these far-flung worlds. Mercury, Venus, Mars, Jupiter, and Saturn are all naked eye planets, and they've been known about for thousands of years. And although Uranus is also actually a naked eye object, at nearly magnitude 6, you need a very dark sky to see it. And early astronomers thought it was just another star. So to recognize Uranus and to see Neptune, you need magnification. Hence the reason why Uranus wasn't discovered until 1781 by William Herschel during his telescopic survey of the heavens. Neptune's discovery just over 60 years later, in 1846, was as a result of a mathematical prediction by Leverrier and Adams. And this was based on a gravitational disturbance of an unseen body on the orbit of Uranus. In other words, Uranus was never where they expected it to be, because it was apparently being pushed and pulled by this unseen object. The search for the planet of Britain, based on Adams' prediction, yielded nothing. Meanwhile, Leverrier got fed up waiting for French astronomers to look for the planet. So he sent his predictions to Gallet at the Berlin Observatory. And it was Gallet who actually observed it that night and within 1 degree of where Leverrier said it would be. Incidentally, Galileo had already seen Neptune through his telescope, but thought it was just a strange blue star. So Uranus and Neptune make up the last 2 of the 8 classical planets. And for a long time, it had been assumed that all the planets formed where we see them today. But that idea is now falling out of favor, and it's all due to the discovery of exoplanets, many of which are found in very strange orbits around their stars. This is thought to be the result of planetary migration and planetary ejection. And if that can happen in exoplanetary systems, perhaps that could have happened in our own solar system, and it might explain some of the oddities about Uranus and Neptune. For example, why are they the size they are? Why aren't they as big as Jupiter and Saturn? And why does Neptune, despite being the outermost planet, have more mass than Uranus, although Uranus is actually slightly bigger? It's always been said that the reason the ice giants didn't grow to the size of the gas giants is because where they formed in the outer reaches of the solar system, there was less material to accrete, and a smaller mass meant they could never manage to attract as much gas as Jupiter and Saturn. However, computer models now show that Uranus and Neptune are actually too big to have formed from the sparse material in the outskirts of the solar system. So what's going on? Well, computer models show us that the planets may have formed a lot closer to the sun, with a large disk of debris around the outermost planet. Now, if Uranus and Neptune formed further in, there would be more material from which to accrete. And if Neptune formed on the inside of Uranus, then that could explain why Neptune is a little more massive than Uranus. And with this model, the Nice model, and there are a number of variations, Jupiter, with its huge gravitational influence, is thought to have moved into a resonance with Saturn. So Jupiter here in green, Saturn here in orange. This would have disturbed the orbits of the outer planets, pushing them away from Jupiter. And it's possible that Saturn had a close encounter with Neptune, kicking it outwards so that it zoomed past Uranus into the disk of debris, scattering it and pushing the leftover material beyond Neptune, which then settled into the sparse ring of Kuiper Belt objects that we see today. Some computer models also show that the only way the solar system ends up with 2 ice giants instead of 1 is if there is a 5th large planet between Saturn. So that would be a 5th large planet between Saturn and the next outer planet. And this fifth planet gets ejected by Jupiter, who is the bully of the solar system, and once again scatters, all the outer debris is scattered as Neptune and Uranus zoom past each other and move into this disk of debris. And then the question is, could this fifth planet be planet 9? Who knows? Well, we probably recognize the ice giants by their color, which is blue, with a hint of green for Uranus. The color stems from the gas methane, which absorbs red light, leaving the bluer wavelengths for us to see. Methane condenses out of the colder atmospheres of the ice giants, whereas it's too warm in the atmospheres of Jupiter and Saturn for this to happen. So their bright and colorful appearances is due to various other gases in their atmospheres. Now, only 2% of the ice giant atmospheres contains methane, but it's enough to produce this gorgeous color. And the rest of the atmosphere is composed of hydrogen and helium, just like it is with Jupiter and Saturn, but there is much less gas overall. In fact, it's only when we look at a diagram like this that shows the relative sizes of the large planets that you realize just how small Uranus and Neptune are when compared to Jupiter and Saturn. And yet they were originally put into the category of gas giants. It was only because of the Voyager mission that it was recognized that they are sufficiently distinct to have their own category of ice giants. Uranus and Neptune appear very similar to one another. Similar color, slightly less blue for Uranus. Similar size, Uranus slightly bigger. Similar mass, Uranus slightly less massive. Similar rotation rates or day lengths. So about 17.25 hours for Uranus and just over 16 hours for Neptune. Similar composition, which means they will probably have similar interiors, and they also have similar, very peculiar magnetic fields. In fact, they're much more like twins than Earth and Venus, which really only have their size and the fact that they're composed of rock in common. There are, however, two main differences between them, and it's these differences that makes each of them unique in our solar system. The first difference is the one we all know and love, in that Uranus is tipped over onto its side. The second is that Uranus doesn't have an internal heat source, which probably accounts for its mostly bland appearance. Let's start with that first main difference. Uranus has a tilt of 98 degrees. That's more than a right angle. Now, here is the South Pole, and you can see that from this arrow, Uranus is rotating in a clockwise direction. It takes your head a little while to get around that, but I can assure you it is a clockwise direction. Whereas, of course, most of the planets rotate in an anti-clockwise direction. So its tilt means that it orbits the sun on its side, effectively rolling along its path as it moves around the sun. A consequence of that is that first one pole and then the other pole faces the sun, so the poles will be in either continuous sunshine or darkness for about 42 years. That's half its 84-year orbit. So at the equinox, ignore this date here, the whole planet is bathed in sunshine, equal day and night. But from this point onwards, as Uranus moves this way in its orbit, the South Pole receives continuous sunshine. As Uranus moves, more and more of the southern hemisphere begins to receive continuous sunshine. More and more of the northern hemisphere receives constant darkness, till you get to the solstice and the entire southern hemisphere receives constant daylight, whereas the whole of the northern hemisphere receives constant darkness, and then it reverses as we go round to the next equinox. There are a number of theories that try to explain the tilt, and most, as you might have guessed, involve an object hitting Uranus. The latest theory suggests a planet twice Earth's mass hit Uranus early in its history, but at an oblique angle, so this would be a glancing blow, tipping it over, but which allowed it to retain its atmosphere, rather than the atmosphere being blasted off into space. However, the collision would have thrown bits of the planet, rocks and ice, into orbit, which would have then coalesced to form moons and rings. And because Uranus by this time was already rotating on its side, gravitational forces and centrifugal forces would have corralled that material to form around the equator, moving in the same direction as Uranus is turning. Now, Neptune has a more normal tilt at about 28.5 degrees. So it's similar to the tilts of Earth and Mars. And this means it'll experience seasons like Earth and Mars. But because Neptune's year is 165 years long, the seasons are very much longer, about 41 years or so. So if you thought the winters in Scotland were long, just try living on Neptune. And the other major difference between Uranus and Neptune is that Uranus doesn't have an internal heat source, in that it doesn't emit more energy than it receives from the sun, whereas Jupiter, Saturn, and Neptune all produce more energy than they receive from the sun. For example, if we take the atmospheric pressure, the atmospheric temperatures for Uranus and Neptune, and we compare them at the 1 bar level, that's the atmospheric pressure at sea level on Earth, they're found to be nearly equal at around -200 degrees centigrade, even though Neptune is much further away from the sun and receives less than half the amount of solar heating that Uranus gets. So Jupiter, Saturn, and Neptune are probably producing heat left over from their formation, and also perhaps from gravitational energy being converted into heat energy from substances falling through their interiors. And this also happens, or is thought to happen, on Neptune, but I'll come back to that a bit later. So why doesn't any of these things apply to Uranus? Well, no one is quite sure, but it may have something to do with being knocked over onto its side. Perhaps this caused the heat source to shut down, or it somehow expelled all the heat, or perhaps the interior is somehow trapping the heat so it cannot escape. So is this why Uranus looks mostly featureless? Could be. And yet it must have some deep internal heat because it has a magnetic field. When Voyager 2 flew past the planet in 1986, it found a bland, featureless, and perhaps, dare I say, boring world. And it was only when Uranus was looked at in the ultraviolet that a circulation pattern showing banding could be seen. Now, 12 years later, in 1998, Hubble took a photograph, and Hubble used infrared light because these wavelengths detect heat, so they can see clouds, which are caused by warm air rising, and you can see plenty of them in the Northern Hemisphere here. Unfortunately, Voyager didn't have an infrared camera, so it couldn't take photographs like this. Now, the South Pole, where it was still summer, can be seen to be bright, and it's bounded by this brighter band called the Southern Collar. The polar cap and collar are thought to be a dense region of frozen methane clouds. It seems that methane deeper in the atmosphere has warmed in response to the summer sunlight and has risen to the colder part of the atmosphere and there cooled into clouds. Now, the North Pole couldn't be seen by Voyager 2, or Hubble until the start of the 21st century. Astronomers wanted to see whether there was a northern cap and collar, just like the southern cap and collar. But as the northern polar regions came into view, they realized that there wasn't. In the years leading up to the equinox, which was in 2007, and this is when the northern hemisphere was moving into spring, clouds began to be noticed quite frequently in the north. So this is 2004. Of course, we saw lots of clouds in the previous photograph, and that was 1998. And then in 2005, we have an enormous cloud noticed. And at this time, the southern polar cap began to dim, although the southern collar remained bright. And then in 2006, the first dark spot was noticed. And then when Uranus reached its equinox in 2007, which is when the equator faces the sun, so that sunlight illuminates the whole planet, and the rings are edge on, and this must be one of my favorite photographs. I think it just looks beautiful. The bright southern collar also began to fade, and the one in the northern hemisphere began to develop. And all this indicates that Uranus was responding to seasonal change as the northern hemisphere was warming up. Now, this photograph was taken by the Keck 2 telescope in 2012. That's a ground-based telescope with adaptive optics, and it uses infrared wavelengths which have penetrated the topmost clouds to show this incredible cloud band beneath. And what hasn't yet been explained is this beautiful scalloped band encircling the equator, which you'll notice is much more noticeable in this side of Uranus than in this side. There are also lots of storm-like convective features, presumably methane clouds that are rising upwards as they are warmed as the northern hemisphere moves towards summer. And they seem to be in the process of forming the northern cap. And hey presto, there it is 2 years later. Although, and I'm not sure whether it's to do with the wavelengths used, but you don't see a separate northern collar here now. And this is 2014. And you can see some enormous and intense storms that Uranus is experiencing. This particular storm was so bright, it could be seen by amateur telescopes. And it's really quite funny because astronomers in the 90s, their telescopes. Modern day astronomers had looked at these sketches and decided that the 19th century astronomers had been seeing things and that the clouds weren't real. Then, just to prove our astronomers wrong, we get an intense storm like this one that amateur astronomers can actually see with their telescopes. And here we have the latest photograph of Uranus with its beautiful north polar cap. Even though storms can be seen in the atmosphere of Uranus, no one quite knows where the energy to drive them is coming from, as it doesn't have an internal heat source like Neptune. And it's so far away from the sun that you wouldn't expect solar heating to have much of an effect. And yet it must do, because the change in its weather coincides with seasonal change and therefore the amount of energy received from the sun. Now, when Voyager flew past Neptune in 1989, it found a huge contrast in its weather compared to Uranus, and astronomers were utterly astounded. When passing Jupiter, Voyager photographed a brightly colored planet. Saturn was a bit more muted, Uranus was bland. Therefore, Neptune was also expected to be featureless as it was even further from the sun. So to come across a world with large and small storms, white clouds zipping around the planet, and the fastest winds in the solar system was totally unexpected. These white clouds are thought to be similar to our cirrus clouds on Earth, but on Neptune they're made of ice crystals of methane. And they must be quite high up in the atmosphere because they cast shadows on the blue cloud deck below. The largest storms are probably high pressure systems and are thought to be vortices in the upper cloud decks, which extend downwards where they may dredge up material as they rotate, possibly hydrogen sulfide. So it's a good job you need breathing apparatus at Neptune because it wouldn't smell very pleasant. And then we have small dark spots, which rotate in the opposite direction and are therefore low pressure systems. Now, when Hubble photographed Neptune a few years later, so this is 1995, the great dark spot had disappeared. And this was a surprise, as they assumed it would be long-lived, like Jupiter's great red spot. Observations have shown that they last perhaps a couple of years or so, and on average appear every 6 or so, although that varies quite a bit. Here we have a succession of photographs by Neptune, by Hubble, sorry, from 1996 to 2002. And they've shown that over time, Neptune's cloud bands in the southern hemisphere here become wider and brighter. Now, these images on the left have been taken by Hubble, and each one a quarter of a rotation, whereas the images on the right have been averaged by a computer to show the progression of the cloud bands increasing in brightness, gradually changing. The increase in brightness seems to be a response to the amount of sunlight received by the planet, which was gradually increasing for the southern hemisphere because the southern summer solstice was approaching. And it was the southern summer solstice was in 2005, which is this image here. And then 6 years later, in 2011, you can see how quickly cloud features have changed. And this seems to be very common with Neptune, that they change very quickly over the entire planet. This photograph shows the first dark spot for about 20 years. The arrow here is pointing to its bright companion clouds, and it seems that these always herald the great dark spots. And this set of images shows the storm dying. And this was the first time that ever been able to watch one of these large storms, these dark spots dying. It was expected to move towards the equator and then to go out in a blaze of white methane clouds, but instead it simply fizzled out. So just yet something else that was unexpected with Neptune. And then here we have the latest images of Neptune. This one with adaptive optics, and this one by Hubble. And you can see a very large storm here in the northern hemisphere, which is experiencing winter. Now, it's the sun that drives the weather on Earth, but could it really affect the weather on planets so far away from the sun? Well, Uranus certainly seems to respond to the meager amount of energy received from the sun. But with Neptune, its internal heat must also play a part, particularly in producing winds which blow faster than on any other planet, reaching speeds of up to 2,100 kilometers an hour, or 1,300 miles an hour at the equator. But even on Uranus, wind speeds reach around 900 kilometers an hour, and this occurs at high latitudes. So we've looked at the atmospheres of the planets. what about their interiors? Well, to try and work out what the planets are made from, it's important to know their densities. And density here on this axis is in grams per cubic centimeter. And if you look at the inner planets, you'll see that they are quite dense. And that's because they're made from a denser material such as rock, and they have cores of metal. Now, Mars is less dense because it has a small core. Mercury, which is a tiny planet, is very dense, denser as Venus and Earth, not far off Earth either, because it has a large iron core. And if you look at the outer planets, you'll see that they are much less dense. Jupiter and Saturn are enormous planets, and if they have a low density, it means they have to be made mostly of the lightest materials in the universe, which are hydrogen and helium. And as an aside, if we look at Saturn, it has a density of 0.69, which is less than the density of water, which is 1. And that is why, if you had a bucket of water big enough, Saturn would float. Uranus and Neptune have similar densities to Jupiter, so they will also be composed of light materials. But because they are much smaller than Jupiter and Saturn, and please note that the planetary sizes here are not to scale, because these two are much smaller than Jupiter and Saturn, they won't be made up solely of hydrogen and helium, but instead will have some denser materials. So we'll have a quick look at Jupiter, and Saturn is thought to have a similar interior. And you can see that we have an area of gaseous hydrogen and helium, which transforms into liquid hydrogen and helium, which transforms into metallic hydrogen, where they think the magnetic fields are generated. So you can see that these planets are made mostly of hydrogen and helium. But the ice giants look very different. The atmosphere consists of a layer of hydrogen and helium, plus that little tiny bit of methane, of course. And it's perhaps around 3,000 kilometers wide. Now, Jupiter, if you look at Jupiter's gaseous atmosphere, well, that's around 21,000 kilometers wide. So that you can see that there is not enough atmosphere in Uranus and Neptune to be squeezed into metallic hydrogen, which is what happens in Jupiter and Saturn. Instead, there is a vast ocean of water, ammonia, and methane called ices. Now, ices is one of these strange astronomical terms. It means volatiles, which are substances that vaporize easily in the presence of heat. And if found at the cloud tops, they would be frozen. Water, ammonia, and methane would usually be found as a gas at the temperatures deep inside the ice giants. But under the pressures found here, they will be squeezed into liquid form, and that's why we have an ocean of these substances. Now, as you move into the interior, the temperatures could reach maybe 5,000 degrees centigrade. And the pressures could reach perhaps 7 million bars, or 7 million times the atmospheric pressure at sea level on Earth. This means that the ocean is going to be very hot and very dense, especially towards the core. Now, this view of the interior is rather simplified, and some recent research has shown it's probably more like this. Although bear in mind that these layers may not be stratified, but blend into each other. Here we have the thin atmosphere of hydrogen and helium with that little bit of methane. And then we have the hot, dense ocean of water, ammonia, and methane ices. Going further into the interior, the temperatures and pressures are so great that eventually the water, ammonia, and methane will break apart. Water can then form electrically charged ions which conduct electricity. Ammonia is thought to do the same thing when it breaks apart. These water and ammonium ions flow freely and form an electrically conducting layer known as the ionic fluid layer. This layer would be convecting because of heat leaking from the core. And if you have an electrically conducting layer that is in motion, this will result in a dynamo action, which in turn would generate a magnetic field. So this is the layer where it is thought the peculiar magnetic fields of Uranus and Neptune are produced. Let's have a quick look at a normal magnetic field, and this is Earth. And the shape of the magnetic field is the same as if Earth had a bar magnet at its center. And you can see that the magnetic axis is offset slightly to the rotation axis, where we also find the north and south geographical poles. So the two are offset by about 11.5 degrees. Now, Earth's magnetic field is generated in the outer liquid iron core. Iron is an electrically conducting substance, and because the outer liquid iron core is in motion due to heat leaking from the solid inner iron core, it forms an electrically conducting layer that generates a dynamo that in turn generates a magnetic field. These are the magnetic fields of Uranus and Neptune. There's the rotation axis, and this is the magnetic axis. Now, Uranus rotation and magnetic axis are about 59 rather than 60 degrees apart. And for Neptune, it's around 47 degrees. In addition, neither magnetic axis goes through the center of the planets, but instead sits in the outer part of their interior oceans. And this is why it is thought that the magnetic fields are generated in this ionic layer, and that this layer must only be about halfway down or so in order to produce the magnetic fields that are away from the center of each of the planets. Now, if this ionic fluid was deeper, a normal magnetic field like Earth's would be produced. So what about this layer? Why doesn't it contribute to the magnetic fields? Well, at this point, pressures are so great that we encounter ice, but in a form that is extremely dense. And this is called superionic ice. Normal ice consists of a six-sided lattice, and water expands as it freezes into this lattice. But it's not strong enough to withstand the immense pressures that you find inside the ice giants, but also in some of their icy moons. So it changes shape into something denser, and this is known as ice 10. Superionic ice is known as ice 18, and it is a solid lattice formed with 4 oxygen atoms at every corner, and then there's another one at the center of each face. Now, these orangey, yellowy blobs in the middle are the hydrogen ions, and these hydrogen ions can move around freely inside like a liquid, which means that the ice would be both a solid and a liquid at the same time. And the ice may even glow black. Now, don't panic with this slide. It's to try and help explain what's going on. So the lower axis is pressure in millions of bars. So this is 1 million bars, or 1 million times the atmospheric pressure at sea level on Earth. And this axis is for temperature in kelvins. The blue line represents Uranus and the red line represents Neptune. And basically what the diagram is showing you is that as you move into the interiors of the ice giants, the temperatures and pressures increase. Now, I'm assuming this fully fluid area is the hot, dense ocean of water, ammonia, and methane. that transforms into the ionic fluid layer near the edge of the superionic ice. And this, of course, is the superionic ice. And there are two forms. So this orangey area is the BCC form, and the yellow area is the FCC form. And I am not going to explain them. Oops. So as we move into the deep interiors, we encounter the BCC form first. And this is thought to have flowing hydrogen ions, so it should be electrically conductive. But as you go even deeper, you encounter the FCC type. And this has a slightly stiffer structure, and the hydrogen ions cannot move as easily. So the FCC type of superionic ice will only be weakly electrically conductive. In addition, it's unlikely to be convecting, probably because of the stiffer arrangement of the lattice, which means that this layer of superionic ice will not contribute to Uranus and Neptune's magnetic fields. Therefore, there is only a small area that will be electrically conductive, plus maybe this tiny bit of the BCC superionic ice. Now, all this is speculation, and it has been developed through experimental techniques and computer modeling. I'm not going to talk about the magnetospheres, you'll be glad to hear, as they are extremely complicated. Uranus's in particular, which corkscrews through space as the planet rolls around the sun. And I think this diagram is utterly astonishing. But what a magnetosphere can do, if you've got a magnetosphere, of course you can have an aurora. And there are plenty of aurorae here that you can see. And what they've done is to add the rings afterwards to orientate us so that you can see the aurorae are nowhere near the poles. And this is because of the huge offset between the magnetic and rotational poles. Now, if you thought superionic ice was strange, what about diamond rain, which sounds extremely exotic? And this should happen on both ice giants. And I've not said much about methane so far, but just like water and ammonia, it will also break apart under the intense pressures and temperatures into carbon and hydrogen. So you'll get clusters of carbon atoms, which will then be squeezed together into a diamond structure, which is the most stable form of carbon under these high pressure conditions. And that's why diamonds on Earth only form deep underground. Diamond is denser than the hot, dense ocean of water, ammonia, and methane, so it would sink towards the planet's core. And diamonds touching other diamonds may clump together and eventually form a diamond layer around the core. If the temperatures are high enough, this diamond layer may transform further into liquid carbon, and you may get diamond bergs floating in the liquid. The formation of diamonds has even been demonstrated under laboratory conditions, so they're pretty sure that this is what goes on inside the ice giants. Now, diamond rain releases gravitational energy, which is converted to heat by friction between the diamonds and the surrounding material as they descend. And this might explain why Neptune emits more heat than it receives from the sun. In fact, more energy than Jupiter and Saturn produce, although it still doesn't explain why Uranus doesn't have the same internal heat source. So if they think diamond rain occurs on Uranus, why doesn't it emit more energy than it receives from the sun? Now, you remember those hydrogen ions that were left floating in the hot, dense ocean here? Well, under the intense pressures that they would experience inside the interiors, they could come together and form pockets of metallic hydrogen, which might be another explanation for the ice giants' bizarre magnetic fields. You put the lot together and you might get something like this. So we have the hydrogen helium atmosphere with a little bit of methane. We have the hot dense ocean of water, ammonia and methane. We've got the ionic fluid layer. Then we've got possibly the formation of diamonds, maybe superionic ice. We've got diamonds, well, whether or not they get to the core through this, somehow I doubt it. Then you've got a core of goodness knows what, and you have these pockets of metallic hydrogen, possibly. Nobody knows. There are lots of ideas, but in fact, currently, there is no model of the interiors of the ice giants that explains all the observations. Now, I'm going to finish quickly with the moons and rings of the ice giants. Uranus and Neptune both have rings just like Jupiter and Saturn, but they are very dark and sparse and are nothing like Saturn's magnificent structure. Uranus has 13 rings. You can see 9 of them here. Voyager found 2 more and Hubble found 2 more since then. And this beautiful bright ring here is being kept in place by the shepherding moons, Ophelia and Cordelia. Uranus has 27 moons. Ignore the bit where it says new and new. This is an old diagram, but it serves my purposes rather nicely, so I've kept it, or I'm using it. So 27 moons, and the innermost 13 are closely associated with the rings, which are here in red. So these moons are very small, same dark color as the rings, and they all orbit very closely to one another. It's thought that there was once a larger moon that strayed too close to Uranus, consequently broke up, and the chunks formed the tiny moons, and the rest made up the inner rings, which are very clumpy. The outer rings, however, are made more dust rather than bits. The 5 major moons of Uranus are thought to have formed from the disk of material that would have surrounded Uranus after the planet was in collision. Titania is Uranus's largest moon, and it's the 8th largest in the solar system. Both Titania and Oberon may have internal oceans. Ariel and Miranda show signs of geological activity, which is quite extraordinary, particularly for Miranda, because Miranda is a very small moon. It's about the size of Enceladus, which would fit comfortably into the United Kingdom. And of course, I had to show this photograph of Miranda because it's got Inverness here. And this is a chasm found on Miranda, along with 2 others. So these are chasms or canyons that are thought to have formed when water inside froze, expanded, and then split the surface. But no one is absolutely sure. I prefer the NASA explanation, which is when the moon was hit by something, it broke apart, and then all the pieces came back together like a jigsaw puzzle gone wrong. And then we have 9 outermost moons, which have very strangely orientated orbits. All orbit in a retrograde fashion, suggesting they are captured moons. Neptune has 4 rings. They are very sparse, only made from dust, and if you put all the material together, it would make something that was only maybe a few kilometers in size. Now, the outer ring is known as the Adam's ring, and it's got these strange arcs within it. These are clumps of material which astronomers would have expected to have smeared out round the ring by now, but they haven't. They're still there. It's not known how the clumps are kept in place. They thought maybe Galatea, which orbits very closely to the Adam's ring, had a hand in it, but now they're not so sure. Neptune has 14 rings. These are the 7 innermost rings, which, unlike most moons and planetary systems, may not have formed when Neptune formed, and you'll see why in a moment. The 7 outer moons are thought to be captured, although only 4 orbit in a retrograde direction, and that includes Triton. Now, Triton is an extraordinary moon. It's a little bigger than Pluto. It has the coldest surface in the solar system at minus 240 degrees centigrade. It orbits closer to Neptune than our moon orbits the Earth, and it is geologically active, which was a huge surprise, just another huge surprise when Voyager flew past these outer planets. Although we know now, of course, that Pluto is active. And the activity is from geysers which cause these dark streaks. When sunlight warms the nitrogen ice, and yes, sunlight will do that even at this distance, because there is a darker coating under the nitrogen ice, it warms from the inside out. The nitrogen ice changes from a gas, and the pressure builds until the nitrogen gas bursts out through the ice, taking with it the tiny sooty particles. And then they produce these tall geysers, maybe 8 kilometers or so high. And then as Triton moves around Neptune, and I love this bit, the plumes leave those trails behind. Nereid is the 3rd largest moon of Neptune and has the most elongated orbit of any moon. Conversely, Triton has the most circular moon orbit of any moon. And Triton was once thought to have been part of a binary pair from the Kuiper belt that strayed too close to Neptune, and Neptune chucked out one and captured the other. That's Triton, and that's why Triton is thought to orbit in the wrong direction. Now, the capture of Triton would have thrown the inner moons into chaos, causing them to collide and break up. Only once Triton's orbit became stable would the material be able to coalesce to form moons. And this is why the inner moons that we see today may not actually be the original moons that formed when Neptune did. And Nereid was probably thrown into its highly eccentric orbit when Triton was captured. We know least about Uranus and Neptune than any of the other planets in the solar system. They are fundamentally different to Jupiter and Saturn. Everything about an ice giant challenges the way we think about the physics and chemistry within these planets. Their formation is not understood, although they apparently require specific conditions and a very narrow time frame in which to develop. And yet they, along with mini Neptunes, are some of the most common types of planets found around other stars. Are they an intermediate stage between perhaps a super-Earth and an ice giant? Nobody knows. And understanding these exoplanets relies on us understanding the ice giants in our own solar system. There are now many planetary astronomers clamoring for a return to at least one of the ice giants. But this probably won't happen anytime soon, because a major issue with missions to the ice giants is the transit time. This means that any mission required to orbit Uranus or Neptune must travel at a slower speed than a spacecraft that would simply perform a flyby. The decade or longer transit times greatly complicate mission design and resource allocation. However, NASA has narrowed down its Discovery program to 4 possible missions to the planets, one of which involves a fly past of Neptune and Triton to be launched in 2026 to take advantage of an alignment between Jupiter, Neptune, and Triton. However, with the discovery of possible life in the atmosphere of Venus, I've got a feeling that they'll choose one of the other missions, which just happens to be one that will examine Venus's atmosphere. So if the Trident mission is chosen, then we might learn a little bit more about Neptune. But overall, it means we're going to have to wait a little bit longer to further our understanding of these extraordinary, exotic, enigmatic, and quite unique worlds. Thank you.
Brilliant, thank you very much. Right, I've got a few questions that have come in. I'm on my phone here. Eric Walker has asked, does it rain methane on these planets? Now, you did mention diamond rain, but is there methane rain?
No, I don't think it does. Because you'll have, it depends on what you mean by rain. There won't be methane rain in the atmosphere. That's unlikely because it's there as a gas. It's too cold really for methane rain. And below the methane cloud deck, there are a couple of other cloud decks, and then you get water, a water cloud deck. So whether it rains proper rain at some point, I don't know. But I don't think the conditions are quite right for rain in the atmospheres. But of course, rain as in liquid rain within the oceans, then yes, that may well happen. But it's, I don't think anybody really knows, so it's not an easy one to answer.
Okay. Rich is wondering what happened to the planet that bashed into Uranus?
That, because it hit at a glancing blow, some of it would have been incorporated into Uranus, but the rest may well have just either disappeared, well, you know, flown off into space, but certainly some of it would have become part of the rings and the moons, but quite possibly not all of it, because the whole thing wouldn't have necessarily been taken up by Uranus, if you like.
Okay, and also from Rich, do the storms form in a similar way to Earth?
Yes, with the high pressure system and low pressure systems, quite possibly. But with the ice giants, the very big storms seem to be more vortex-like, where they extend a long way, so possibly more like our hurricanes. I'm not absolutely sure, but I think it may be similar to that. But I wouldn't be surprised if you can still get high pressure, low pressure systems. So it could be similar to that. But the thing with the ice giants is that these storms can apparently wander all the way across the planet, whereas on the planets of Jupiter and Saturn, they tend to be constrained between the bands. But that doesn't happen with Uranus and Neptune. Not sure why.
Les Grosvenor, more of a comment really, saying Uranus 2012 scallops look like vortices, which she did kind of...
Well, the scalloped band around the equator. Yeah, it does. When you consider the strange markings that you've got, the cyclones that you've got around the poles of Saturn, for example, it makes you think about that, but maybe as a continuous band. But no, it's something that they're still looking at, and maybe your explanation could be part of it. Who knows?
Eric Walker asked, are there aurorae on these planets? You did mention aurorae on your last.
Yes, there certainly are on Uranus. I haven't found any pictures of them taking place on Neptune, but I'm pretty sure they must occur there too. There's certainly something called radio aurorae on both of them. But yeah, I'm pretty sure you'll get an aurora on Neptune. But again, it won't be near the poles. It'll be anywhere on the surface where the magnetic field is happening to poke out, if you like. So I mean, it's an absolutely bizarre system. But yeah, I'm sure you'll get aurorae on both of them.
Okay, Rich is also asking, did the methane form by the effects of pressure, as there's no energy for chemical reactions?
You mean the methane in the atmosphere or inside?
I'm not sure what he meant. He might be able to pop up in the chat and clarify that, but he doesn't say specifically, he's just saying.
Yeah, I just meant the
There you go.
methane generally, really, rather than, you know, but because it's in the clouds and in the bottom or the lower parts of the core, isn't it? There just seems a lot of it, and I thought,
Yeah.
you know, there's no
I don't
chemical
know.
energy sort of thing to form it.
I don't know how much would be found in the interiors. I know that they talk about 2% in the atmosphere. So there must be more found in the interior. But a lot of it is to do with the fact that these planets are formed right in the outer, well, maybe not quite so far out as it was originally assumed, but nevertheless, they are formed in an area of the solar system where there's a lot of ice. And the further out you go, the more the type of ices that you get with the colder areas. So that's why you've got ammonia, but methane will be part of that too. So it'll be probably incorporated with the building blocks of the ice, bits of ice that in part made these ice giants. And I would imagine that that is where the methane has come from. But a lot of it's to do with temperatures. And then certainly on the outside, because it's so cold, you've got more methane. And then as you go on the inside, because of the way the planet's formed, I'm pretty sure that that must be how they've ended up with a lot of methane and ammonia and also water on the inside, more so than Jupiter and Saturn, which would have formed a little further in. They still would have been built up mostly of ice, or a lot of ice, but it's just different places in the solar system where they're formed. So I think something like that anyway. These questions are hard.
Making you work tonight.
Yes.
Pete is asking, how much water do astronomers think there is on Uranus and Neptune?
How much water? Again, it'll be in the amount of ice that has been accumulated. I don't know. I really don't know. I couldn't give you numbers. Yeah, I couldn't give you numbers. I think a lot of it is that they don't know. They are really unsure of quantities. And I know that something that I've read recently suggests that they don't even know the ratio between rock and ice inside these planets, which is why when I was talking about the interiors, I spoke about all of it being speculation, because they cannot constrain these ratios. So I don't think they know, but I'm sure there'd be something somewhere that would tell us or give us an idea how much water was there. But no, not off the top of my head, sorry.
And the last one, could the gravitational push-pull of their moons contribute to any heating?
I don't think that is possible now. I think the moons really are too small to do an awful lot, apart from Triton. But when you consider the size of the planets, no tidal heating, no, it couldn't, because you're looking at a lot of gaseous atmosphere, and this wouldn't, so the heating involved wouldn't penetrate as far as inside. So if you're thinking about the amount of energy released, then no, definitely not. And I don't think it would contribute to any other form of tidal heating at all, because you're looking at a planet with a huge gaseous atmosphere. okay, it's not as big as Jupiter and Saturn, but you've still got big atmospheres. No, tidal heating more for rocky bodies, but it's also very unlikely to contribute to the heat source emitted by the planets. And certainly, of course, Uranus doesn't emit any extra heat at all. So I hope that answers something.
Absolutely. Well, I think that's all the questions that came in. So I shall hand back over to Pete.
Thank you, Donna.
Next bit. Thank you very much.
Hi.
Pauline.
Can you hear me okay?
Yeah.
Yep, you can hear me. That's good. I wasn't in for the practice. Sorry, I wasn't here to greet you, Pauline. Have a
Okay.
little family thing we have to deal with here tonight, and I've been running late from work. But it was quite nice. I came as an attendee, and it's nice to just sit back and listen to the talk rather than see what's going on Zoom. Let's say it's the second time I've heard it, and I'm sure everyone enjoyed it. I know I enjoyed it for the second time tonight, and it's really, really interesting. And as you say, there's so many questions, isn't there, that we don't know about Uranus and Neptune.
Exactly.
But hopefully we'll get out there sometime with some probes and see what's going on. So what I would like to do is I want to say thank you very much once again for coming along. You've probably got a couple of these now because it's not the first time you've been to Circle.
I have. There it is. Look.
Well, you're going to be getting another one. I'm not sure if it's the same design, but if not, you'll have a pair if it is.
Thank you.
No worries. Thank you so much for giving up your time for us once again. It was really, really appreciated.
You're very welcome.
Thank you very much. Please stay on for the second half if you can. And if you want to, you're quite welcome to come into the members gathering. We'll have a good old natter in there if you want to later on, if you got the time.
Thank you.
But that's up to yourself.
Okay. Probably disappear by then.
Yeah, that's fine. That's fine. But we'll meet again soon. Okay.
Right.
Yeah. Well, I apologise to everyone else for not being here earlier on. But thanks, Rich, for standing in at very, very short notice. An hour or two before we were meant to open up. What we'll do, as I say, we're going to go into a little break now, then we'll come back with the second half. So please don't go away. Going to have a little 10-minute break. When we come back, we will be having Space News with Stuart Brooks. Then Mick will be giving us our tour of the sky at night, more sky at night. A little bit of club news from myself, and then we'll go over into the members gathering and have a good old chin wag over there. Okay. So just for the next 10 minutes, we'll come back just after 10, but just after 10 to. We'll see you for the second half. Thank you very much. Muted. Okay, welcome back to the second half of the Sigma meeting. We will be kicking off any minute now, hopefully, with Stuart with the space news. Are you there, Stuart?
Yeah.
Yeah, good to see you. Okay, over to you, my friend.
Okay. Welcome to Space News, and I'll just put up the screen.
I'll see we've got you.
Okay. Right, what I've chosen for this month, there's a few activities. There's quite a lot going on to actually choose from. So I've picked these just for their interest and the development from previous months. The training for Artemis program lunar landings, which includes the new suit, SpaceX activities, the ocean monitoring satellite, Russian space activities, and China's plan for 2024, and also an interesting one, Mars for sale. It's 50 years since humans set foot on the moon, and NASA are developing 2 brand new suits for the Artemis program. The new spacesuit for walking and working on the moon is the Exploration Extra Vehicle Unit, XEMU. Now, a lot of this has been overlooked because of the late, or overshadowed by the delayed hardware, the Orion capsule and the much delayed Space Launch System rocket. But a lot of the work is now coming to an end this year to start using it. And this is the spacesuit. And you can see there, this was as it was set out in 2019. And the 5 suits are being produced for Artemis 3 mission. One for design verification, which should end this year in December. One for qualification testing, one for testing in orbit, and 2 for walking on the moon in 2024 for the Artemis 3 mission. Now, this is a fairly simple layout of what the bits and pieces of the suit are, as you can see there. There's also, as you see top left, there's also an internal cooling garment being completed, and that's the first prototype is nearly completed. And the backpack, which you can see, the portable life support system shown there, is also being updated. Now, at the same time, there is also the suit for exiting or leaving the Earth and returning to Earth, called the Orion Crew Survival System, which looks like that. And this is for launch and re-entry and emergency situations during the Artemis missions. Now, the astronauts have started training in the lunar pool. I've got 3 shots here showing them doing their tasks. I've got one here which should come up, which will show you a little bit more when it starts. This runs for a little while, but I'll show you, it just gives you a better idea what the suit looks like. I won't put it onto full screen, because if it does, it throws me out of screen share and I have to go and get it back in again. As you see, it's quite bulky. I'll let them go down and come back up, and then we'll move on. It's not something to move about very quickly in, but it's supposed to be an improvement on the previous suit.
We can't seem to see the video, Stuart.
Can you not?
No, so I wouldn't worry too much.
All right, sorry about that. Well, what I can do, I can get it. No, okay. It was actually showing on my screen, but not. Okay, sorry about that. But you saw the stills of it. The other activity I was looking at was SpaceX launches and their activities. On the 6th of October, they did another launch of 60 satellites. On the 7th of October, the Starman, if you remember, makes its first close approach with Mars. On the 10th of October, NASA announces the crew mission, which was scheduled to launch on Falcon 9 on 31st October, was delayed until the 14th of November. And the 11th of October, Starship SN8 receives 3 Raptor engines. And on the 26th of October, SpaceX launches another 60 satellites. So if we look, SpaceX launches its 60 satellites, is SpaceX's 13th batch of Starlink satellites to orbit. That makes 700 into orbit to date as part of their mega constellation project. It's its 17th mission so far in 2020, and its 94th Falcon 9 flight to date. It was the 3rd launch and landing of that particular Falcon 9. The first one was when it took the first astronauts for NASA in May, and also a communication satellite for the South Korean military. And approximately 9 minutes after launch, the booster's first stage came back to Earth, landing on one of SpaceX's drone ships in the Atlantic Ocean. And that's its launch. And that's its recovery, or at least after its recovery, it's taken back to base. Now, on the 7th of October, the spacesuit-clad mannequin in the Tesla Roadster, which launched in February 2018 on a debut flight of SpaceX's powerful Falcon Heavy rocket, made its first close approach with Mars. It passed within 0.05 astronomical units, or under 5 million miles of Mars. And it circles the sun once every 557 Earth days. And as of the 7th of October, it has covered nearly 1.3 billion miles in space. It will eventually impact into Venus or Earth, likely within the next few tens of millions of years, a 2018 orbit modeling study has determined. Chances of an Earth or Venus impact to the next million years are just 6% and 2.5% respectively. And the Falcon Heavy has since launched 2 more successful missions, both of them operational flights. The communications satellite Arabsat 6A in April 2019 and delivered 2 dozen payloads to orbit for a variety of customers 2 months later. And that's, if you remember, we had that last year, the Tesla Roadster. Now, NASA announced that Crew 1 mission, which was scheduled to launch on a Falcon 9 on the 31st of October from Kennedy Space Center, will now launch on the 14th of November. The time to complete hardware testing and data reviews in evaluation of a Falcon 9 first stage engine gas generators during a recent non-NASA mission launch attempt caused a problem with the turbo machinery gas generator, or rising pressure of that, and which was part of a launch on the 2nd of October, and it was cancelled within 2 seconds of launching. And that decided then that they would delay any further launches of these new rockets. The other missions had gone before, had actually launched and been successful. These were launches for the first time, and therefore they delayed them. The GPS-3 one that was launched or delayed, launched yesterday successfully. So that one is now clear, and it's now waiting for the Crew 1 mission to go. and that's Crew 1, which we're all ready to launch in the their capsule. Now, they're what's called Expedition 64. Currently in the International Space Station is Expedition 63. When they when the a later one, which I'll show you, which is a Russian one, arrives there, they will spend 7 days together, and the 63 will return to Earth. And another success for SpaceX is on the 11th of October, installation of the 3 Raptor engines that will power Starship's SN8 test flight started, and that's installed in the engines. And on the 20th of October, the 3 Raptor engines of SN8 Starship prototype carried out a successful brief static fire. And there's due a launch to 11 miles either the end of this month or the next month. And that's the 3 engines now installed in the Starship. And they launched another on the 24th of October, another 60 satellites. And this was a 100th Falcon successful mission. And that's its launch. A little bit of history. The first mission for the Falcon, which was a Falcon 1, was in 2008. And it failed on its first 3 launch attempts. And it's interesting that if it had failed on the next one, according to Elon Musk, the company would have folded. But fortunately, the next 2 were successful and led the way for Falcon 9, which is responsible for 95 of SpaceX's 100 successful launches to date. 3 flights have also been performed by Falcon Heavy, which we mentioned earlier, which consists of 3 modified Falcon first stages strapped together with a central core topped by a second stage and payload. Now, SpaceX has launched, or should I say landed, first stage boosters 63 times and pre-flown rockets 45 times, but not everyone has been successful. So in addition to the 3 failures of the Falcon 1s, there on June 2015, a Falcon 9 broke apart 2.5 minutes after launch, a cargo mission to the International Space Station. And in September 2016, a Falcon 9 was destroyed on the pad during a static fire test. However, since September 2016, 71 successful liftoffs have occurred, which is quite a feat for this particular rocket, but it's going to be replaced by Starship once Starship becomes available. Another thing that happened this month is the Sentinel-6 Michael Freilich ocean monitoring satellite came up at a media meeting to say there was going to be a launch on the 10th of November, which has since been delayed to the 21st of November. This is also going to be launched by SpaceX. It's the first of 2 Copernicus Sentinel-6 JSON-CS, which is a continuity of service satellites launched in 5 years apart and will extend a nearly 30-year data test of ocean data. After launch, the satellite will collect sea level measurements down to a few centimeters across 90% of the world's ocean. And there's the Sentinel 6. It's named after Michael Freilich, who was a former director of NASA's Earth Scientific Division. Soyuz launched an American astronaut and 2 Russian cosmonauts to the ISS in Soyuz MS-17, just ahead of and to extend 20 years of continuous human presence in Earth orbit. And this was the first crewed use of an ultra-fast flight plan which saw the Soyuz arrive at the space station within 3 hours of its launch, rather than following an earlier expedited 6-hour track or 2-day path. The 2-orbit rendezvous had been previously modelled and tested with Progress cargo vehicles. And Soyuz MS-17 is Russia's 63rd Soyuz spacecraft to launch to the International Space Station since 2000, and 146 to fly since the first Soyuz mission in 1967. It is the 100th spacecraft to launch a crew toward the space station, including the Soyuz MS-10 in flight abort in 2018. So both the Russians and SpaceX are doing quite well with their number of launches. And that's the Soyuz launch on the 14th of October. And that's the MS-17 arriving at the International Space Station. The Russian space agency Roscosmos has announced it aims to develop a 2-stage rocket called the Amur, and it gets its name from the base that it's actually launched from, Amur in Russia, whose first stage will return to Earth for vertical powered landings like those performed by SpaceX. And this is a breakdown of the rocket. It's smaller than SpaceX and powered by 5 engines compared to Falcon's 9. But one thing it's doing, it's using methane as a fuel as opposed to liquid oxygen and kerosene, which the Falcon's using. But SpaceX is actually changing that for the Starship when that comes along to use methane instead of the kerosene. It's also, when it's launched, it will come back to a land base and not a sea-based landing like SpaceX, although the Russians did have a barge for recovering early on, and they were re-looking at it to see whether it was going to be used again, but they said that's still an option, but they're not intending to use it at the moment. China is also looking to develop more with the moon. It's got 2 space vehicles on the moon at the moment, which is Chang'e 4 land and the U-2 rover, and these are 2 selfies they've taken, or taken by each other, so not necessarily selfies. And it is now preparing to launch another mission this year. Chang'e 5 will land near Mons Unca, a mountain overlooking a huge basaltic lunar plain called Oceanus Procellarum, and it will bring back samples from the lunar surface, the first new material from the moon in more than 4 decades. Scientists are eager to get new samples which would join material returned by Apollo astronauts and Soviet robots, and hopefully answer questions about the formation of both the moon and Earth. And it's expected to launch by the end of this year. And that's NASA's image of the area where Chang'e 5 moon sample return mission is supposed to take place. Chang'e 6, the ancient impact, according to a press conference given by State Council Information Office. Such material represents some of the oldest samples taken from the lunar surface. A date has not yet been given for this launch. Chang'e 7 will soon follow and conduct comprehensive surveys around the moon's south pole, studying terrain and landforms. The final currently planned mission is Chang'e 8, which is expected to test key technologies that will lay the groundwork for a crewed mission, or a crewed research mission based on the moon. As yet, the Chinese Space Agency has yet to announce the exact timeline of these future missions. Now, Mars for Sale, this is an interesting one, which I picked up in the newspaper, then followed it up. On the 17th of October, it's reported that a GP from Hampshire with a laser pointer has a firm belief that he owns Mars. Every week for the past 10 years, Dr. Davis, 54, has gone outside into his garden in Hampshire and pointed a laser at Mars. Between 5 and 20 minutes later, billions of photons have hit the surface, and occasionally one has liberated a molecule of CO2 from the soil. Dr. Davis said it's a nugatory amount, but that doesn't matter. It's structurally trivial, but not legally trivial. Under one interpretation of international law, to gain possession of unclaimed land requires simply showing you have improved it. International law says that for rough, barren land, you have to just do some early things to exert control and make it ready for future habitation. Dr. Davis said, and he is giving the rough, barren land of Mars an atmosphere. Now, when I first saw that, I thought that was another thing like Ted Hughes, the guy who wanted to prove that the Earth was flat. But when I looked into it, and that's Dr. Davis doing his laser pointer, what he's trying to do, and that's it, there's his website, which you can look at. He doesn't want to own Mars, nor believes it's sensible, but there is a good legal case to own it. The Outer Space Treaty was drafted in 1967 as it was the foundation of space law, primary aim to stop weaponization of space. And what he wants to do is to re-examine and strengthen the space treaty. A high court rejected his claim to the UN, and he's now trying to go to the Court of Appeal. The Outer Space Treaty guarantees to keep space as common land. And on the 13th of October, a group of nations signed the Artemis Accord, dictating how further missions to the moon should be run. It was the US, Japan, Australia, Canada, Italy, and the UAE. The Accord appears to be a direct attack on the Outer Space Treaty. In particular, the Accord defines safety zones around moon bases, which looks like a land grab. The Outer Space Treaty states that you can't appropriate land by claim, use, occupation, or any other means. A safety zone is appropriation by other means. Signatories do not include Russia or China, which is a bit of a setback, because Russia, although a partner with NASA on ISS, did not sign, and the US Congress banned NASA from working with China in 2011. So Artemis Accord, in one sense, is an attempt to update the Outer Space Treaty, but it's being done unilaterally, and therefore there's a major problem going to arise later on. And when you look at China has now armed satellites, Russia has armed satellites, and the US has armed satellites. So it's a problem in the making. And if anyone wants to buy some Mars, I'm not sure if this has come up, is this? Perhaps Peter, tell me if you
We're
can
still
see
just seeing the picture of his website.
Right, it's not come up, but that's his website that that you couldn't go into. So if you look up Dr. Davis and Mars sale, you'll find out all the information on how to purchase a part of Mars. And that's all for now. Thank you.
Okay, thanks, Stuart. Yeah, I'm quite interested. That's international law. I don't think it's interplanetary law, though, is it? So,
so
it's not interplanetary law, is it?
Well, no, because that's the problem. There isn't any.
Perhaps we need the Federation of Planets.
Yeah.
Okay, Stuart, that's great. Thank you very much. I can't see any questions come up, so you're lucky. You've got
good.
You've got something. What do you mean good?
Yeah, I'm just trying to find a pointer to stop the share. There you go.
Yeah. Okay, that's brilliant. Okay, thanks again, Stuart. And Mick, if you're ready, we'll kick off with the Moray Sky at Night.
Yep. If you just give me a second. I'll share that. Oh, yeah.
We got you. I'm not seeing you at the minute. Aha.
Right, there we go. Should have Stellarium there.
Yeah, I don't think I'm seeing you though, Mick.
Are you not?
No, have you got your video on?
Yep. I have. Stopped it again. It's on.
Stuart, if you want to just turn your video off, that might help.
Oh, sorry. Yeah.
I can see myself on the.
We got you now. There you are.
Yep. Okay. Cool.
Okay, over to you, my man.
Excellent. Thank you. Thank you very much, Pete. Thanks, Stuart. Let me just get what's set up here. Okay, so hello everybody, welcome to the November edition of Sigma's Murray Sky at Night tour. Firstly, as usual, we shall have a look at the planets. So I've gone here to the 10th of November, and at 6:30 in the morning, it's going to be the closest time you're going to be able to see Mercury as it's heading to its greatest elongation at 5 p.m. on the 10th. But you should be able to see it in the early morning of the 10th, 11th, 12th, certainly any days either side of that. But please remember to be very careful if you're looking at Mercury at this time in the morning, because it's just before the sun's rising. So if you're using any telescope or binoculars, cameras, make sure you're well away from the sun before it rises above the horizon, or it will cause permanent damage. So moving forward to the 12th, you can see the moon's coming down here to be within 3 degrees of Venus, and continuing into the 13th in the morning, you get a nice little cluster spike out Venus, the moon and Mercury just before sunrise. Again, be very, very careful of that sunrise time and keep all your cameras and certainly eyes well away from the sun rising. So in November, we have the peaks of 2 meteor showers, the first of which is the Northern Torrid meteor shower, which began in mid-October. That reaches a maximum on the 13th at round about midday. So to get the best viewing of it, you're probably better going to the 13th at night. So if I take that to 2100, and I'll show you where the Torrids is. If we find Orion here, come up to Aldebaran, which is in Taurus, and the radiant of the Northern Torrid shower is going to be in this area here. So obviously anywhere 20-30 degrees away from it, you should catch some meteors. We're only expecting a low rate of about 5 meters per hour. But after dark, a set waning crescent moon is going to make viewing quite favourable this year. This shower gradually tails off into December, on the 10th of December. So that's the Taurids. The other meteor shower is the Leonids, which peaks on the 17th. And we're going to have to go round to the northeast, and you can just about make out here, this is the head of Leo coming up. So obviously if there's any meteors emanating from Leo in this direction, northerly direction, you should see them. But just to confirm where we are, I'll go to 11:30 on the 17th. And the radiant for the Leonids is going to be in this area here. So anywhere around there. And this shower is associated with the comet 55P Tempel-Tuttle. It's got a relatively short period of activity, just from the 5th to the 29th of November, with a maximum around the 17th, 18th. I think the actual peak is 10:53 on the 17th, so obviously broad daylight, you're unlikely to see any meteors unless they're really bright. High rates of meteors were seen in 1999, 2001 and 2002, and believe it or not, they reached about 3,000 meteors per hour. However, this year, it's only expected to be around 15, but it's well worth having a look out for them. Moving to the, where are we, 18, go to 4 o'clock, to the south. So a little photo opportunity round about sunset time, just after sunset. You see the moon, Jupiter, Saturn here. And over the next 3 nights, it's going to be even closer on the 19th, and then moving past on the 20th. And if we continue that fashion following the moon to the 25th, it's going to be within 5 degrees of Mars. And on to the 30th, follow it around a little bit later. It's going to be on the 30th, right next to Aldebaran. So that's the planets for November. let's have a wee look at some deep space objects now. So instead of touring a single constellation, which I have done in the past couple of months, what I'm going to do tonight is look at a selection of deep sky targets in a few areas you might not have considered. There's going to be an example of each of the major classes of deep sky objects, apart from a globular cluster, because this class doesn't have any major players that are pretty well suited this month. So I'll go back to the middle of the month. Where am I going? 23, yeah. 2300. And what I'm going to do is start at, well, just swing it around to the northwest and go up to Cassiopeia. So let's get that in the center. And what we're going to look for is NGC 129, one of Cassiopeia's fine open clusters. Now there's quite a lot of open clusters up here. This one in particular, if you take the second V of Cassiopeia and come in between these two stars, the center star and Beta, round about here. I'm probably not going to get the, yeah, I did get it, look, amazing. Right, we'll do that one. So here we have NGC 129, open cluster, quite rich and impressive looking cluster with an integrated magnitude of 6.5 from the combined brightness of around 200 stars. But it's positioned right slap bang in the middle of the Milky Way, as we've seen. If I just zoom back out for a second, you can see it's slap bang in the middle of the Milky Way, but it is in the North Circumpolar constellation of Cassiopeia, so you can see this all year round. But being as it is slap bang in the middle of the Milky Way, there's an awful lot of stars around about it, so it's quite hard to differentiate which ones are actually part of this open cluster. But a pair of 10 by 50 binoculars will show it as a small round haze, while a small telescope shows an obvious triangle of brighter 9th magnitude stars south of its centre. Going up to a 10-inch telescope can reveal as many as 80 stars, which have a large range of brightness. So our next stop, we will head for NGC 1333, which is told a pretty reflection nebula in Perseus. So Perseus across the other side of the sky pretty much. If we come down the left leg to the bottom here, just orientate that. And what we need to do is come across to Omicron Persei and head some 3.3 degrees to the west-southwest, round about here. And yet again, it flags up something completely different, but it is the same one, which I'll prove in a second. Pardon me. So this is a colourful star-forming nebula complex. As I say, it's a reflection nebula, and a reflection nebula is basically clouds of interstellar dust, which might reflect the light of a nearby star or stars. The energy from the nearby stars is insufficient to ionize the gas of the nebula to create an emission nebula, but it's enough to give sufficient scattering to make dust visible. As you can see, it's a mishmash of mainly blue reflection nebulosity, dark nebulosity, and a few intense areas of glowing red emission. It can be found with a 6-inch telescope as an elongated haze, but a 10-inch telescope can tease out some brightness differences. For our next one, we're heading towards Taurus for NGC 1514. Just zoom out slightly here. And we are going to be heading east around 8.5 degrees. So that's round about here-ish. And what we'll do is zoom in. If you use the two stars here as pointers, and come down about twice the distance again, and then a little bit further south, I'm sure I'm pretty much nearly on it-ish. Oh, I've just missed it. Look. So crystal ball nebula, NGC, excuse me, NGC 1514. It's Taurus's one and only bright planetary nebula, but it looks like it's a pretty good one. Shining at a magnitude 10.9, it's tough to spot in a small telescope, but its center star has a magnitude of 9.4. But the brightness of that star can make the nebula quite hard to observe. A 5-inch telescope operating at about 100 times magnification should be sufficient to snare it. If you use a no triple I filter, which is a narrow band filter specially designed for the observation of diffuse and planetary nebula, it should suppress the brightness of the central star and heighten the nebula's contrast, lifting it out of the sky background. A 12-inch telescope can reveal some structure in the nebula, even at low powers though. Okay, so for our next one, I'll zoom right out. We are going to head to a bit familiar territory. Now, you probably notice I'm heading south, which is not always a good thing in astronomy, but we'll get there. So we're heading south to Orion, and we look to the bottom right for Rigel and for our next target. Our next target, though, is actually across in its neighbouring constellation of Eridanus, the river. So if we just home in on this a little bit and move up to the northwest about 3 degrees towards this bright star here, Kurzi Al Hwaza 1. Never heard of that before. Anyhow, this is, I'm sure a lot of you recognise, the Witch Head Nebula. It's actually, you'd have to turn your head upside down actually to see, because this is kind of the chin, nose, forehead, I think, something like that. When you see it the right way up on a picture on the internet, it's kind of obvious, but it's not so obvious here. So this is a large, excuse me, this is a large reflection nebula. You see it's covering quite a bit of sky here, 3 degrees by about 1 degree, meaning that it's about, I've wrote it down here, it's about 50 light years in length. It's kind of overshadowed by the glare from Rigel, but astronomers reckon that Rigel and the Witch Head Nebula are both the same distance, which is about 900 light years, and that Rigel is the source that's illuminating the Witch's Head. Images show its pretty blue colour owing to its dusk grains reflecting Rigel's blue-white output. So our next target, I'm going to zoom out again. For our next target, it's quite a little bit away. It's about 30 degrees away. We're heading for quite an easier, I'm told, and colourful double star, 32 Eridani. What I do is if you use Safe and Rigel as the pointers and follow these up, as I say, about 30 degrees, get to this star here, 32 Eridani. Let's zoom in on that. Doesn't look particularly fantastic, but I'll just keep zooming in. And we will see. It was a bit fluky when I was doing this earlier on because I just kept going in, and then I found that it does actually split the stars apart. So you can see, so the components shine by a combined magnitude of 4.4, so finding it shouldn't be a big issue. The primary stars are magnitude 5, class G yellow giant star, given a big great golden hue, and it's separated from a magnitude 6.1 class A2 secondary star with a blue colouring by quite a wide 6.8 arc seconds. A small telescope, just 3-inch class, will easily show black sky between the two stars. But for some nice colour contrast, you want to go up to a 6 to an 8-inch telescope. Okay, that's that one. And next, okay, this should be fun. Next, for the last two targets, we're going to have to go really low in Eridanus now, the river, to find these two. Now, you see a lot of you thinking there's going to be a lot of murk down there, but you never know. And once you see what I'm going to show you, it could be worth having a little, making a bit of effort to try and find them. But there's two absolutely magnificent galaxies. If you follow Eridanus round, all the way around to here till it kind of flattens out here, we have Tau 5 and Tau 4. If I get this centered a bit and zoom in, as I say, this is like really taking you out of your comfort zone because there's probably going to be quite a lot of atmosphere down here, but I think it's going to be worth a shot. If we go up to the northwest of Tau 4 by 2.5 degrees, just here, which is not going to, hasn't done all day. Why is it doing it now? Right, center that, zoom in. Here we have, I think you'll agree, a fantastic face-on spiral galaxy. So deep amateur images show multiple spiral arms, more than the normal 2 to 4. As you can see, it's oriented to face-on, and its spiral arms actually have quite a low surface brightness, making the galaxy quite hard to spot compared to if it was inclined or edge-on. But it's relatively bright at magnitude 9.9, though its light is spread over quite a substantial area. It's at a distance of 60 million light years, which equates to a very large physical diameter of 200,000 light years, which places it midway in size between the Milky Way and Andromeda Galaxy M31. A 46-inch telescope will show us a round and diffuse glow spanning about 2 to 3 minutes. Its wonderful spiral arms are tough to trace, even from southern climates. So for the UK, you'll probably want to look at this through, wait for a 16-inch telescope. However, that's for viewing. Imagers should fare a much better chance at this. It's got to be a prime target for anybody who's logging into any of the remote facilities that are springing up around the world, like SLU or iTelescope, for example. Could be one to add to your list to go and have a look at. And lastly, we staying in the same area. We just head 2.5 degrees northeast to NGC 1300, a classic barred spiral galaxy. So although it's half a magnitude fainter than the previous target, it should be slightly easier to detect because of its bright bar. Completely different looking galaxy, but I think you'll agree it's one of the finest barred spirals in the entire sky. And it equals our previous target in awesomeness as far as I'm concerned. So deep amateur images reveal two well-defined spiral arms that fold back from each end of the magnificent bar, curling around it and wrapping around each other. This lies about 69 million light years, about the same distance as NGC 1232 we just looked at. And both are prime members of the Eridanus cluster of galaxies, which boasts a membership of about 200. So it appears noticeably smaller in the sky than NGC 1232, but physically, excuse me, it's perhaps as large as 150,000 light years across. A 12 to 14 inch telescope hints at the spiral arms on a clear night under dark skies, obviously. And being where it is so low in the down there in the murk, it could be fun. And that's me for this month. I will catch you all in the meeting room afterwards and see you again in January.
Okay, thank you very much, Mick. Yeah, as Mick said there, he won't be doing this next month because it's our usual Christmas quiz will be happening then. I'll go through that in a moment. So just to finish off with a little bit of club news from myself here now. As I say, as Mick mentioned there, we'll be having our gathering after this one, straight after this. So I'll keep this as short as I possibly can. We get over there and maybe have a little drink together. So to say, what I'm going to do in a minute, I'm going to put the link to that gathering in the chat, or Rich will if he's got it. To say, once we end up here, just click that link and it should be able to take you straight in. Yep, that's Rich has just put it in already. Almost like we're organized, isn't it? And to say, what we're going to do, I've got some some breakout rooms in there as well, so we can have a little bit of a practice ready for the Christmas quiz next month, just to show you how the breakout rooms work, and you can have a play around in them. Or if you're in there and you want to have a private talk to someone, let me know and I can put you into a room together and you can just talk away there. Okay, as long as you don't talk about me. But don't forget, I can come in and have a listen. Yeah, as I say, the Christmas quiz, we're going to go for it. Going to give it a go. The way it's going to happen is, hey, Kevin's busy in the background at the minute putting all the questions together, I'm sure, if he hasn't already finished it, because he's pretty well up on that sort of thing, and say very well organized with that. You will receive a registration email. Now, this Christmas quiz, we will run it in a meeting, not in a webinar like this here, so you will all be able to see each other if you want to, and be able to hear each other. All the instructions are actually in the newsletter that I sent out in November, and I'll put them out again in December. And also I'll have a run through on the night to show you how it works, and I'll have a practice run as well. Okay, but don't forget, don't be afraid to come along thinking, oh, everyone will be able to see me. So I know how it is. This isn't suited to everybody. We know that. We totally understand that. You have total control over your cameras. Okay, so if you don't want your camera on, you can leave your camera off and just your name will appear. You don't even have to have your microphone on when you're in the main room. You can turn that on and off. You know, if you go into the breakout rooms, obviously you want to discuss with your team the questions and answers, you can turn your microphone on there, and when you come back to the main room, you can turn it off again. Totally under your control. We cannot turn your cameras on or your microphones on. We can ask you to, but it's all up to you. So don't be afraid to come along. As I say, it's just the same as being in the hall. We just have a good old chat, you know, have a good laugh and try and get these questions right. And this is obviously going to be open to all the other clubs as well. I'll be sending you out the registration email. So I'll be doing that in the next couple of weeks. Sorry, yeah, sort of middle of next month, I'll probably put that out, beginning of the middle of next month. What you'll need to do is to fill that registration in and just send it back. Okay, it's all self-explanatory when you get it. The only difference is you'll see one box that says organization. If you're going to be in a team, what I should do is put your team name in the organization so I can link you all together and put you all into the same room. Okay, so I will control all that, sending you into your rooms and back out your rooms again, so you're something else you're not got to worry about. We will be having another practice run, the committee, and we'll be having a practice run with that very soon, so hopefully it'll all run smoothly. Hopefully. If it doesn't, we'll just go into the main room and get the mince pies out and the sherry. Okay, that sounds good to me. Yep, as I say, full instructions on that is actually in the newsletter anyway. Our YouTube channel, as I say, that's still up and running. This meeting will go on to that, but I'm only going to make these meetings now available to members rather than being public. Okay, I'll probably put the public events up there, but the reason being, I don't see why we should make it free to everybody when you're paying your membership to come and see these meetings. Okay, they'll probably go on in a year's time or something like that, when when it's not so sort of on demand there. So okay, I'm going to say it's more of a members benefit, and the link to that will go out, and the link to the previous meeting will go out in the next month's newsletter. That makes sense. I've seen Helen put in the chat your photographs. So as Mick said there, there's quite a few photograph opportunities coming up. Even if you've not got a telescope, you can have a go at taking photographs of the moon and Jupiter and Saturn there. Okay, and if you do, send them in. There's a link once again in the newsletter and on the website to send your photographs in, and we'll get them up in the Flickr site and also on the web page as well, on the front page. So you can get your picture on the Signal web page. Don't forget to invite a friend. If you've got anyone you think you might be interested in joining Sigma, just give them a nudge, get their email to me, and I'll send them an invite to the to the next meeting we got. Okay. The how-to, as I say, once again, I've still not had time to put anything together to get them up and running, but I will do my best. Honestly, I will do my best to try and get some of that done. For the new members, we've done some how-to sections, you know, basic astronomy ideas and information. You can find them on the YouTube channel. We recorded all the ones we've done so far, so there's a lot of information in there. But as I will, if we can get some time together between us, we will get this running again. Okay. Once again, if there's anything from me, you can let me know in a few minutes when we get into the gathering. Either send me an email if there's anything you think we could improve on, or if there's just anything you want to sort of say about the club, because once again, I say it is your club, it's not my club, it's your club, and we will run it to the best we can for you. So with that, the next meeting, let's say, is the quiz. All the information is in the newsletter for that one, and I'll give you some more later on in the December newsletter. Keep an eye on your post box as well. Towards the middle of December, there might be something coming through for you. Okay, a little early Christmas present, perhaps. Okay. So say with that, I want to thank Pauline for that wonderful talk. I've seen it twice, and I think you'll agree it's an absolutely fantastic, fascinating talk. Donna, for once again handling the Q&As as well as you do. Stuart, for your space news. I'm still not sure about this owning Mars. We're shining a laser at it. Maybe we'll go around that GP's house and shine some lasers at his garden. Maybe we can own his house. Nick for the Sky at Night. Rich for actually standing in for me early on this evening, and also running the show until I arrived. And for your good selves for joining us and making it all worthwhile us putting this together. So with that, we'll see you all in a few minutes over in the gathering. Good night for now.